All right, everybody, we're going to do 3.3 graphs with holes and variations of asymptotes. So in this section, we look at rational functions whose graphs have holes, do not have a vertical asymptote, or have a slanted asymptote. Okay, so holes and graphs of rationals, where did those come from? Graphs of rational functions do not contain any points on their vertical asymptotes, since rational functions are not defined by x values. So in other words, if there's an asymptote there, the hole can't exist because you're not even crossing it. So additionally, it is possible for a graph of a rational function to exclude a point which is not a vertical asymptote, so where there's an actual hole in the graph. All right, so there are different ways to find this. So first of all, what you'd want to do, because in general we're going to be graphing these at the same time, we want to find the domain. So remember, we do the domain before we simplify it and everything. So first of all, I see that I can simplify the bottom, or factor out the bottom, so that way I can see what my domain is going to be. So my domain cannot have -3, can't have 3. So -infinity to -3, -3 to 3, and 3 to infinity. So that's good. Now what we're going to do, our next step is to actually simplify this, reduce it. And if we reduce it, you see that you can cross out this x plus 3, leaving 1 in the numerator, and x minus 3 in the denominator. Okay? Remember that 1 is in the numerator. A lot of people make that mistake, so be careful on that. Now, what you want to define before the hole is you want to define the vertical asymptote. The reason why you want to do this is because the vertical asymptote comes first. If your hole were supposed to be on that vertical asymptote, then you don't have to worry about the hole. So the vertical asymptote is x equals 3. And now we can do our hole. So our hole actually comes from what is crossed off. And what we crossed off was an x plus 3. So we're going to say x plus 3, set that equal to 0, and solve. Now, hole is a coordinate point, so be very careful on that. So that means the x value is -3. We have to find the y value because this is a coordinate pair. The way to find the y value is to plug into the reduced form. You do not plug into the original because, as you can see, we would get a 0 over 0. So always do it into the reduced form. So we have 1 over negative. So I'll put the negative out front, 6. All right, great. Now, what I want you to do is we're going to look at the y-intercept, or x-intercept. X-intercept first. Remember that the x-intercept is setting the numerator to 0. Now, you always do this in the reduced one. And if you look at the numerator, the numerator can never be 0. So we have no x-intercepts. How do we find the y-intercept again? We find it by plugging in 0 for x. And that is a coordinate, so 0, -1/3. Okay, now we also have to, just like in the last section, look at our horizontal asymptotes. And as you can see, we're looking at an x over an x squared, which means our bottom is a larger exponent. So we have a horizontal asymptote at y equals 0. And now we're able to graph. Okay, I'm going to graph all my points first and my vertical asymptotes. So I have a vertical asymptote at 3, 1, 2, 3. I have a hole at -3, 1, 6. So maybe right here. Okay, I have a y-intercept at 0, negative 1/3. Negative 1/3 is closer to 1. Okay, and we're done, right? Because then here is our horizontal asymptote. Now, just like we learned in the last section, we can either plot a point or we could say, well, I know here this is coming closer to our horizontal asymptote. These have to cross, and then it comes down close to that vertical asymptote. Now, if you're wondering if it's on this side or this side, remember what kind of vertical asymptote is it? This is to the first, so it's odd. Remember we talked about this last section? And odd goes in opposite directions. And you're done. Okay. Now we'll do this one. Let's try this one out. So here we're not going to have a vertical asymptote because it says we wouldn't. Now this is why I know something's up. Don't forget, this is not the difference of squares, so I cannot separate that. So my domain. Well, if I look, can the denominator ever equal 0? No, I can't square anything, add it to 9 to give me 0. So our domain is negative infinity to infinity. Well, that also means that there are no vertical asymptotes. And because there was nothing to cross out, I have no holes. Now I need to look at my x-intercept and my y-intercept. X-intercept, of course, again, is where you set your numerator equal to 0 and solve. So the numerator equals 0 at negative 1. Of course, the y value to that is 0. The y-intercept, if we set our x's to 0, we get 1/9. Now, lots of times we stop here, but don't forget we need the horizontal asymptote. And just like the one above, our denominator looks bigger than our numerator. So we have a horizontal asymptote at 0. All right. Let's plot our point. So at negative 1, 0. And at 0, 1/9. Somewhere like that. Now here's the tricky part. We have a horizontal asymptote there. Now here's what's going to happen. We know that this x-intercept is to the first, so it crosses, right? So it's going to cross here. Well, that makes sense because it would come here, right, guys? Now, here's where you need to watch out, because even though we tend to want to go down, we know that there is a horizontal asymptote right here. So at some point, this is going to come back up and get close. Okay? We don't know where, unless we plugged in child, but we know at some point it's going to come up because of that horizontal asymptote. This one right here, okay, we could keep going, I guess, up, but we know it needs to go to this horizontal asymptote. We also know it can't come back down because we would have another x-intercept, but we don't. So I know that I'm going to get close to that horizontal asymptote. And we're done. All right. Now we did where y equals 0 and y equals the leading coefficient for horizontal asymptotes. But what happens when we don't have a horizontal asymptote? What is that? Well, that's what we call the slanted asymptote. So when we do this, we have to actually do long division. Okay, I know some of you hate that and stuff, but that's the way we do it. Okay, So more than likely we're going to focus on the linear slanted asymptotes, okay? So let's look at this function, x squared minus 4 all over x plus 1. In this case, we say that the line y equals x minus 1 is a slanted asymptote. Okay, so as you can see right here, I'll show you how to solve this one down below. But there's a slanted asymptote, which I'm going to graph, and you will have to graph, in which that our graph will come close to that on opposite sides. This is also referred to as an oblique asymptote. Okay. So the line y equals mx plus b is called a slanted asymptote when you know that your numerator is larger than your denominator. Okay, so how do we find these? Well, the truth is, like I said, here we do division, or in this case, long division. Okay, so to do the long division, remember that your denominator is the divisor. It's what's on the outside. So 1 minus x, and then inside is our x squared minus 4x plus 2. Okay. So if you want, guys, what I'm going to actually do is rearrange that. So it's negative x plus 1, because remember, I'm looking at how do I match these two. So what do I multiply negative x by to get to x squared? Well, that would be a negative x. Then I multiply. Negative x times negative x is a positive x squared. Negative x times positive 1 is a negative x. And then remember, you subtract straight down. Or if you want, change each sign and add straight down. So that's 0, and that's negative 3x. Bring down the 2. Okay, and we do it all over again. What do you multiply negative x by to get to negative 3? Well, I multiply it by a positive 3. And you can see, because 3 times negative x is negative 3x. And 3 times 1 is 3. Now, I can subtract straight down, or I can add the opposite and add straight down and get negative 1. And as you can see, I'm all done, right? I can't make x look like negative 1. And it's okay that there's a remainder. What that means is that there is a slanted asymptote at the equation y equals negative x plus 3. All right, next one. If you guys notice right here, okay, our numerator is larger than our denominator, so we're going to have a slanted asymptote. The good thing is we can actually simplify the top and the bottom. Well, the bottom's already simplified. But then we cross out, right? Leaving us x plus 2 over 1. Well, what's anything divided by itself? Or anything divided by 1 is itself, correct? So actually, we don't have to do any long division because we know there's a slanted asymptote. We defined that at the beginning. And so there's a slanted asymptote at y equals x plus 2. Again, we know that we don't have to do any long division because the denominator is 1. Okay. Last one to practice this long division. Okay. So again, I know that there's a slanted asymptote somewhere because our numerator is larger. So now I'm going to set this up. X squared minus 4 on the outside. Now remember, guys, when you do long division, you have to have each of the terms in there. So plus 0x squared plus 0x plus 1. What do you multiply x squared by to get to x cubed? We multiply by x. Then we multiply x cubed minus 4x. Oh, and that actually goes over here, right? That one was missing. Minus 4x. Okay. Now, subtract straight down or add the opposites. So you get 0, 0, and then 4x. Bring down the 1. Can we make an x squared look like an x? No, we can't multiply anything by x squared to get to x, so we're done. Can't go any further, so there is a slanted asymptote at y equals x. Now, very careful, okay? Once your remainder has a smaller exponent than your divisor, you're done. You don't have to go any further. All right, there we practiced some long division to help us graph. Now let's do some graphing, okay? A rational function may have a horizontal asymptote or a slanted asymptote, but not both, because it's one or the other, right? Let's take a second to update our steps for graphing in section 3.1. Okay, remember we did domain, we reduced, we do our x-intercepts, y-intercepts, vertical asymptotes, horizontal asymptotes. In this case, now we're gonna also do holes, right? And then we start plotting. And then sometimes we have to plot an extra point just to see. X-intercepts, we have to figure out if they're touching or crossing. And then your asymptotes, vertical asymptotes, we started to realize that they could be even or odd, and evens go the same way, or odds go different ways. So let's see what we can do to help us graph. All right, domain. Well, what can't x be? X can't be 1, so negative infinity to 1, 1 to infinity. Then our x-intercept. Well, what makes that equal 0? So if you want, you can do the quadratic formula, right? We can say on the side 3x squared minus 2x plus 1 equals 0. And you will find that it is imaginary, it's complex. So in that case, there is none. And you can try that quadratic formula now. Y-intercept is when x is 0. And then we get, if we plug in 0, we get 1 over negative 1, which is negative 1. Vertical asymptotes. There is a vertical asymptote, as you can see right in that denominator, x equals 1. And it's to the first, so I might point out that it's odd. Okay. And there, if we look at holes, there was nothing crossed out, so there's no holes. And now we need to look at horizontal asymptote or slanted asymptote. So I'm going to add on the SA. So we look, our numerator is greater than our denominator, which means we have to do the long division. I'm going to move this up so you guys can see my work. I'm going to work on the side just so I can put what it equals over here. So I have x minus 1 outside. So 3x squared minus 2x plus 1. What do you multiply x by to get to 3x squared? We multiply by 3x squared. And 3x times negative 1 is a negative 3x. All right, we can subtract straight down or add the opposite. So that gives us x. Bring down. What do you multiply x by to get to x? Well, I multiply that by 1. Remember, you know when to stop when it's less than the exponent. This is the same, so I have to keep going. 1 times x is x. 1 times negative 1 is negative 1. Add the opposite, so I get 2. I can't do anything there, so I stop. So my slanted asymptote is at 3x plus 1. All right. Let me do this in color so we can see what's going on. So I have a y-intercept at 0, -1, a vertical asymptote at 1. All right, now the slanted, we do want this to be perfect, or at least try to, because we're not an actual 10 by 10 graph right now. I'm just sketching it out. So how do you graph a linear equation? Well, we start with the y-intercept, which is at 1, and we use our slope, which is 3 over 1. And I'm also going to go the other way, down 3 over 1. Okay, I'm going to use a ruler or a straight edge so I can get the slanted asymptote correctly. All right, now, first let's start out by, since we know that down here there is a y-intercept, I know that somehow the graph is going to look like this, because we're going to hug those asymptotes. And this actually should be dotted, right? Because it's a slanted asymptote. So now, knowing that the vertical asymptote was odd, since this one's going down, this one must be going up. And I know I'm going to hug those asymptotes and you're done. If it was even, I would have been down here. Good job, guys. All right, one more. All right, so on this one, guys, we have a couple issues, right? First, if we look at domain, we need to make sure that we have the denominator in the lowest form, right? So we can just factor out, we get x plus 2, x plus 1. Okay, so I know my domain is -infinity to -1, -1 to 2, and oh, wrong order. By the way, people make this mistake all the time. This is -2 and this is -1. What comes first? Okay, I've seen that a bunch of times, guys, so make sure you're in order. Okay, so this should be -infinity to -2, -2 to -1, and -1 to infinity. All right, here, you know how we've been doing x-intercepts and then y-intercepts and then vertical asymptotes and holes? Well, actually, after you reduce, make sure that you're looking at your holes and your x-intercepts more clearly. And we have an issue, right? Because the only way to find out the vertical asymptotes and the holes are to reduce it. And that top equation right there is an x cubed, which means what we need to do is do synthetic division to allow us to see how the top is broken up, okay? Now, if we are only looking at that it could cross out one of these two, then you're only going to have to try those two. So let's try synthetic with -2. We would have 2, 5, 4, and 1. Remember, bring down, multiply, add, multiply, add, multiply, add. So this one did not work. So let's see if we can do the other one. -1, 2, 5, 4, and 1. So bring down, multiply, add, multiply, add, multiply, add. So yes, this worked. So what does that mean? That means we have x plus 1 times, and remember, this is our remainder, our constant, so x to the first, x squared. So we have 2x squared plus 3x plus 1. So as you can see, we can cross out this x minus 1. So we have a vertical asymptote at x equals, I don't know why I put a parenthesis there, guys. X equals -2 and a whole. Remember, take what you crossed out, set it equal to 0. So we have a whole at -1. Do you remember how to find the y value? To find the y value, you plug it into the x of your reduced one. So we're going to plug -1 into on top and on the bottom. When you plug in -1, we actually get the value of, let's check this, right? So ready? 2 times -1 squared plus 3 times -1 plus 1, 0. Oh, so we have a whole at -1, 0. Guys, if you realize that is also y-intercept, x-intercept, sorry, x-intercept. But you can't call it an x-intercept if it's already whole. So that's why I would say do your vertical asymptotes and your wholes beforehand. Because now when we do our x-intercepts, we do not have to worry about that -1. Okay? But when we look at this and we solve, do the quadratic formula, right? Set this equal to 0. We can use the quadratic formula and we get 1/2. So we can check that again. I'll do this work this time because I'm second guessing myself. So -b plus or minus the square root of b squared minus 4 times a times c all over 2a. Well, that's 1, so that's the square root of 1. We get -3 plus or minus 1 all over 4. Okay, so we would get x equals -4 over 4 is -1, which we've already indicated is a whole. And we get x equals -3 plus 1 is -2. -2 over 4 is -1/2. So again, I dimmed my quadratic formula to find my x-intercepts. Now this one's already a whole, so I can cross it out. So we have an x-intercept at -1/2, 0. Y-intercept is at, well, plug in, go to your original right here. So it's 1/2, 0, 1/2. Okay, before we do our horizontal or slanted, let's go back up for a second. That vertical asymptote, that's to the first, so it's odd. And the x-intercept is to the first because we would have a quadratic and a quadratic, a binomial and a different binomial. So that would be an odd, so it crosses. Okay. And then we have our whole that we crossed out was also to the first, so it crosses. Okay. Now let's do our horizontal and our slanted asymptote. So this we have to do our long division. We get Let's make sure that you are doing it from the simplified one because that's easier. Now, what's great about this, guys, is x plus 2, correct? So we could totally do synthetic if you wanted, or you could do long division. That's going to be up to you. I'll stick with the long division since that's what we've been practicing. So x plus 2 is on the outside. 2x squared plus 3x plus 1. What do you multiply x by? It's 2x squared. 2x. Let's see, 2x and 2 is 4x. Subtract straight down or add the opposite ones. So that would be a negative x, bring down positive 1. What do you multiply x by to get to negative x? You get multiplied by negative 1, negative x, negative 2. Add the opposite. We get 3. Okay, so we're done there. That means we have a slanted asymptote at y equals 2x minus 1. Now I want to point this out, and I hope you can see it on my dot cam here. All of my conclusion is right here. All of my work is on a separate part of my paper. So I don't confuse everything. Because once you start messing everything together, you don't remember what's your answer and what's your work. So lots of times, guys, I will divide my paper up into 2. So I keep my work on one side and my answer stuff on the other. Because now I am going to start graphing. All right, so we have a vertical asymptote at negative 2. 1, 2. And that's odd, so remember they're going in separate ways. We have a hole at negative 1, 0. Make sure it looks like a hole. We have an x-intercept at 1/2, 0. And we have a y-intercept at 1/2. And we have a slanted asymptote at y-intercept is negative 1, and we go up 2 over 1. I'm going to go the same thing, so down 2 over 1. Okay, and there are 2. All right, so how does this work? Well, right away, I know what's going on here, right? So I know somehow it's going to cross over. And at this intercept, it crosses. So we got to come back up here, and at that hole, it crosses. It stays close to the vertical asymptote. Now we know the vertical asymptote is odd. So if this one is going up, this one must be going down. And then we hug those asymptotes. Now, guys, what I'm going to do right now is I'm actually going to graph this on a graphing paper, graphing calculator, so you can see what I'm talking about, okay? I know that you cannot use a graphing calculator on your test, but that doesn't mean you can't use a graphing calculator to check your answers for your homework or your practice work. You want to see what is going on so you know how to do it correctly, and then you can focus on what you're doing without the graphing calculator. So 3x plus 2. What did I do to myself? Sorry, guys, I'm wasting time. If you feel confident, just stop the video right now, or you can see what this says. Wow, what is going on? I'm rushing. There we go. Plus 4x plus 1 divided by x squared plus 3x plus 2. I'm going to make sure my window's in the middle, and then I'm going to go out if I need to, okay? All right, now watch. I'm gonna zoom out just so you can see the bottom part of that. See how, oops, sorry, it's glary. Huh? There we go. You see it? Does that look like our graph? It does. So you can double check your work on the graphing calculator. Of course, don't depend on it. Take it step by step and make sure you've reasoned out why you're doing certain things, okay? All right, guys, enjoy the practice.